Hello everyone, I am Yang Zhou from Visual Computing Research Center, Shenzhen University. I'm so glad to present our work High-Fidelity Text Transfer using Multi-Scale Depth-Aware Diffusion. Textures are a key component of 3D assets. In this work, our goal is to transfer the appearance of a textured mesh to a target shape. The challenge of this problem lies in two folds. First, the transferred texture must match the correct semantics. Second, we need high-quality texture details in the transferred results. Previous work tries to transfer textures through geometric correspondences, but often suffer from distortion issues. Another category trains texture generation models using large datasets, but encounters poor generalization and low texture quality. Recently, with the emergence of diffusion model, new methods of text generation have been developed. For example, texture generates textures view by view by using pre-trained text-to-image models. 0123 series fine-tune diffusion models to generate viewpoint-wise consistent images, but they are limited by the training data and suffering from poor generalization and low quality. TextPainter performs texture fusion at each time step during denoising to simulate the sampling of the entire texture map. While improving the view consistency, it may cause blurry artifacts. Paint3D trains a series of encoders and the diffusion models directly on texture maps, which is also limited by the training data and lacks high-quality texture details. In summary, despite the progress, recent diffusion-based methods still face severe challenges. Addressing these problems, we propose to use pre-trained diffusion models and introduce depth-aware KV injection and multi-sampling mechanisms to improve their texture quality. And we construct a multi-scale diffusion-based framework with consistency loss to resolve the inconsistency issue. For the pre-trained diffusion model, we chose the famous latent diffusion models for our text transfer. Previous work has shown that the self-attention features inside the denoising unit can be used to represent image style or appearance. This technique is called KV injection. Using the KV features of the reference image, similarity is calculated based on the spatial information of the generated image, and then the visual information from the reference image is re-aggregated. Based on stable diffusion and KV injection, our pipeline is like this. Given a target and a reference mesh, we first generate a coarse but consistent texture at 2 scales. Then this coarse texture is refined through iterative optimization to produce the final result. To enhance efficiency, in the first stage, we actually mosaic the rendered views into a single image. The corresponding depth images are also rendered and stitched, serving as geometric condition. Next, let's dig into the details of text generation. We first map the stitched multi-view image into the latent space. Then, the depth images are input as geometric conditions to the text trans module, which generates a transferred multi-view image. Then we update the UV map of the target shape and get a low-resolution coarse texture. Next, we render the target multi-view image as the input for the second round of text transfer and acquire a coarse texture in high resolution. Here's the detailed architecture of the text trans module. The key here includes using ControlNet to extract geometric features from depth maps. And we also use local attention to avoid inconsistency. Using local attention is because our input is a stitched multi-view image. To avoid confusion between different viewpoints, we introduce a mask corresponding to each view, retaining only the attention weights of the corresponding view. Then we use KV injection to copy the appearance features from the reference. To ensure correct semantic correspondences, we use ControlNet to acquire depth-aware attention features, so that the attention computation accounts for the geometry of the reference and the target meshes. So in the first stage, we generate the coarse texture in 2 scales. Then let's see how we refine it with high-quality details. Since now we have textures for both the reference and the target, we can use differential rendering to get high-quality single-view images. Then we use the same text trans module to iteratively transfer the appearance for each single view. During the update of the texture map, a consistency loss is introduced to reduce artifacts. Specifically, we use morphological manipulation to identify the regions that needs to be updated and those should be fixed, as well as the region boundaries. A consistency loss is thus introduced upon the identified masks. Here we visualize the new effect of the new terms. We can see that without the consistency loss, many artifacts can be seen in the UV map. And without boundary loss, seams are still there. And without fixed loss, some pixels are updated wrongly. And our full terms effectively solve all these artifacts. For more details, please refer to our paper. We also found that in the refinement, when the coarse texture differs a lot from the reference, a single optimization cannot achieve ideal generation. We thus use a multi-sampling process to optimize the generated views for several rounds. Here we chose 4 as the default number of iterations. Now let's see our results. Here on the left, we show the results of transferring the same texture onto different shapes. On the right, we transfer different textures onto the same geometry. Next, we show the generation result at different stages of our multi-scale framework, demonstrating the improvements of each stage. Here are our results on other categories. For comparison, we chose 3 recent diffusion-based methods. In this example, you can see texture shows obvious inconsistency issues. TextPanda exits noticeable text blurry. Panda3D loses the style of the reference texture, while our results are consistent across all viewpoints. For this example, both texture and the TextPanda show clear seam issues, while Panda3D again loses the style of the reference. Here again, texture fails to fully adhere to the reference. TextPanda has obvious blurry artifacts. Panda3D captures the semantics of the reference but cannot generate a consistent style. Our method faithfully reproduces the reference texture while generating clear local details. Here are more comparisons. For a better evaluation, we conducted a user study. 37 users are involved and 740 results are collected. Our method is significantly preferred by users over competitors. Next is our ablation study. First, we compare the effects of different view numbers stitched in the generation phase. We found using 9 views effectively avoids many issues. Next is the ablation on depth-aware attention and local attention mask. We can see that removing depth awareness results in roundly geometry for the target shape. The first one gives a totally round target geometry without, and the second one loses the arm of the chair. Removing local attention leads to inferences from other views, causing semantic inconsistency of components, such as the chair seat or text blurring as shown in the second example. Additionally, our approach achieved effective cross-scenario text transfer without requiring model fine-tuning. Here we show transfer results from the 3D reconstruction of real-world objects. In conclusion, this paper proposes a novel multi-scale 3D text transfer framework. We leverage pre-trained diffusion models with geometrically constrained cavity injection, ensuring high fidelity in texture representation and correct semantics. And a novel consistency loss is introduced for reducing artifacts in UV-map update. Although promising, our method has limitations related to depth map accuracy, and we also have minor detail losses due to the diffusion VAE compared to the references. We leave this as future work. Thank you for your listening. Our code is available on project page. You're welcome to follow. Thank you.